physics students. Today we're going to talk about a new topic, power. So this is some new information, so you may want to take some notes. So get out your notebooks and get ready to learn. Okay, so in terms of physics, let's talk about what is power. Power in physics is defined as work done in a given time interval, or the rate at which work is done, or energy is transformed. That's energy transforming from potential energy to kinetic energy, or kinetic energy into non-mechanical energy. So a definition of power is equal to work divided by time. So if you want to talk about the unit of power, since work is measured in joules, time is measured in seconds, that is a joule per second. So 1 joule of work done in 1 second is the basic unit of power. That is defined as the watt, signified with a capital W. So now this is going to cause a bit of confusion. Do not confuse the unit of watts, capital W, with the formula variable for work, lowercase w. So when you write the formula, you're going to have a W in there as work. That is not a watt. Be careful about getting those things confused. So the formula is power is equal to work divided by time. Again, W and work and W and watt. Don't get them confused. So work is also force times displacement. So if we substitute that in, power can also be defined as force times displacement divided by time. But if you remember from chapter 2, displacement divided by time is also equal to the average velocity. So sometimes we can define, or we can also define power as force divided by the object's velocity, as long as that velocity is constant. All right, so let's see how this works with a problem. So I'll give you a second to copy this down. I went ahead and did my step 1 of the 5-step physics problem solving system. Freddie is going to lift a 125 kilogram box and place it on top of a shelf that is 2.2 meters high, and he's going to do that in 2.4 seconds. What's the minimum power he is required to generate? So you might want to pause here for a minute to get that problem written down in your notebook before we continue. Okay, now that you're back, interesting that we say the minimum power he's required to generate, because remember our one definition was force times velocity. So if he would raise this at a faster velocity, that would take more power. So we're trying to say at a minimum, if he was trying to if he moved this thing very slowly, what would be the minimum power that he needs to produce? Okay, so as you can see, I've got my drawing. Here's this 125 kilogram box. He's going to raise it 2.2 meters in 2.4 seconds. If he is going to lift this box, he's going to have to apply a force that's equal to the weight force of the box. So let's take a look at that. And what's the weight force? We know that's always going to be mass times gravity. So we have 125 times a negative 9.81, which is going to make the weight force of the box 1,226.25 newtons. Excuse me while I get used to my new facilities here. So that means he's going to have to apply that much force in order to move the box upward. So he's going to have to apply a force of 1,226.25 newtons. So now remembering what our definition of power was, power is equal to the work done in the time interval. And again, work is force times displacement. So that's force times displacement over time. So we know the force he needs to apply is 1,226.25 newtons. He's going to move that through a displacement of 2.2 meters. And he's going to do that in a time interval of 2.4 seconds. So doing that calculation, I got 1,226.25 times the 2.2 meters divided by the 2.4 seconds gives me a average power of 1,124.06 watts. Okay, so again, simple problem giving us the amount of watts. Let's try another problem. This one's a little more complicated. Specifications for a building say the elevator must be able to travel at a minimum of 3 meters per second with a maximum capacity of 1,800 kilograms. That's passengers and the mass of the elevator. If the total resisting forces in the elevator, friction and what other forces, is 4,000 newtons, what size motor is needed to meet these specifications? Again, you might want to pause here and take a minute to get this information written down. Okay, let's see how we need to attack this problem. I'm going to move this up so I have a little more room to draw. Okay, so first off, we know that okay, let's erase that. All right, so we know that there's a weight force holding this down, and we also know that there's some type of friction or restricting forces working against us, and we want to be able to apply a force that's going to raise this elevator traveling with a velocity equal to, let's remember the number, equal to 3 meters per second. Okay, so we want a velocity equal to 3 meters per second. So again, going back to our formulas for power, one of the formulas is power is equal to force times velocity. So this applied force, in order to travel at a constant velocity, has to be equal to, I know that's back from the last chapter on Newton's laws. In order to travel with a constant velocity, the applied force must equal the weight force and this resisting force. So the weight force we know was mg, so that's 1800 times 9.81, and this resisting force was 4,000 newtons. So my 1800 times my negative 9.81 gives me a total weight force of 17,658 newtons plus the 400 resisting force, or 4,000 resisting force, gives me a total applied force needed to keep this thing in a constant velocity upward of 21,658. Okay, so now we know the force needed, and we know the velocity that we want this to travel at. So power is equal to the force, 658 newtons, times a velocity of 3 meters per second, gives me a power of 64,975 watts. So the size of the motor would probably be 65 kilowatts. Okay, 6,000, again, 1,000 kilowatts, or 1,000 watts make a kilowatt, so 6,497.5 watts, about 600 or about 65 kilowatts.